Thank you all for being here today. We're going to talk about speaker circuits, specifically how they work with fire alarm systems. Some of this will be kind of similar to how other speakers like intercoms or car radios or things like that work. But for the most part, we're really going to focus in on fire alarm systems specifically. So to get started, I'm going to quickly review what we've talked about with some of the basic electrical principles. We've talked about volt, amps, and ohms many times. And I want to remember that, or remind you that voltage is the pressure of the electricity pushing through the wire. The amperage is how much is making it through. And the resistance has a direct relationship with that amperage. So as the resistance increases, which is the ohms, it's going to allow less and less amperage to make it through the circuit. And then the opposite's true. As the resistance decreases and there's less resistance on the circuit, more current will be able to flow through that. We've talked about that a lot in the example with the water hose, being the voltage is the pressure of the water traveling through the hose. The amperage is how much water makes it through, and the ohms are the things that are slowing it down, whether there's sand or mud in the water or in the water hose, or if there's something clamping on it, squeezing down around the outside of it, or if you have some kind of valve restricting flow. Well, today we're going to add one more thing to that. And imagine that water is flowing past a paddle wheel of sorts, kind of like an old grain mill or an electric dam. And that's going to be the measurement of power, also known as wattage. So if you have a small amount of voltage, small amount of amperage flowing past that paddle wheel, it might not turn it at all, or it'll turn it very slowly. The more pressure you get pushing on it, and the more volume you get pushing on it, the faster and more easily that wheel is going to turn. And that's what wattage is. It's the amount of power coming out of it, the amount of power being produced. And so it's really just a look at combining voltage and amps into one measurement so that we can understand the actual rate the power is being transferred. And that matters for audio circuits because amplifiers, they're rated in watts. The watts tell us how much work the amplifier can do. Oftentimes, the amplifiers that we work with will be one of two sizes. That's a 50 watt or 125 watt amplifier. And that tells us how much that amplifier is capable of, how many devices we can put on it, how much sound output we're able to get out of those devices is going to be determined by that size of that amplifier. For the Gamewell FCI systems that we put in, we pretty much always use distributed audio, which just means we're putting amplifiers all around the building. We're not doing a bulk audio, which is where you have a massive amplifier in like a fire control center, and then that one massive amplifier is powering everything. We distribute it and use a bunch of smaller amplifiers. The Gamewell FCI, they're all the distributed amplifiers of that style. They're all 50 watt amplifiers, and we can put up to 4 of those in a cabinet. So one cabinet can produce 200 watts of power distributed out among different circuits. As far as the Silent Night and the Fahrenheit goes, we're actually putting individual amplifiers distributed around that are in 50 watt or 125 watt configurations. And those 50 watt and 125 watt amplifiers have multiple circuits that come out of them. But it's not 4 circuits that are 125 watts each. It's one amplifier that's 125 watts, and we can divide it up any way we want among the 4 circuits, as long as the 4 circuits don't exceed what the amp is rated for. And that kind of gets us into the second point about amplifiers have 2 limits to the devices on their circuits. The first one's the wattage, like we were just talking about. That's how the amps are rated. That's if you want to know how many watts you have on your circuit or on your amplifier, you look at your plans, you count up the ones you have on your circuit that you pulled, and we're putting wattage taps on every drawing we do. So if it's at a half watt, a quarter watt, or 1 watt or 2 watt, you add all those up, and that's how much wattage you have on that circuit. It's just simple addition. And then you take however many circuits you have on that amp and you add those together, and that's your total wattage for the amplifier. So depending on what amp you're using, that's going to determine how much you can have being drawn out of it. The other limit that we've had on amplifiers is going to be the length of the circuits that we have. There's a few things that go into what actually determines how long a circuit can be, because every circuit's a little different. The first thing is going to be what load you have on the circuit, because if you have a higher load on the circuit, you're not going to be able to go as far before you run out. The other thing is going to be what gauge wire you're using. The thicker the gauge of wire, the more power it's able to easily transfer. The thinner you get the gauge, the shorter it's going to be able to go. And I think it was the third I said. We've got the load on the circuit. I don't know. I had 3 things, but I'm only coming up with 2 at the moment. Sorry about that. But it's going to be that distance. Oh, the voltage putting out. That's what the other one is. That's a big deal. So our speaker circuits can have 2 separate voltages. We have 25 volt speaker circuits or 70 volt. If you look on the back of system sensor type devices that have the speaker in it, you'll notice you've got either 2 or 3 settings, depending on if you're working with a device that's only a speaker or a speaker and a strobe. I'm going to talk about the device that's only a speaker, so I can talk about just the 2 settings that matter for speakers. The first of which is your volt. You're selecting which volt it is. Are you on a 25 volt system or a 70 volt system? And then the second one is what wattage you're actually using. As far as the 25 or 70 volt selection goes, that's going to be a universal setting that you're going to have to select for. It'll be the same for every single device on the job. And that's really going to be determined by which amplifiers we're using. For Gamewell FCI systems, it's actually a different physical amplifier. So the 25 volt amplifiers, even though they're 50 watts, both the 25 volt and the 70 in the case of Gamewell, but they're different part numbers. They're different physical parts. So we can't just change it mid-job or something. It's whatever we order and install, that's what you're going to be using. So you need to make sure you know what kind of amplifiers you're using on the job to make sure you're getting that setting correct. I usually try to include it on the drawings to make it as easy as possible to find out. With Silent Night systems, all of their 50 watt amplifiers, and this is true for Fahrenheit and Silent Night side, all the 50 watt amplifiers are selectable 25 volt or 70 volt in programming, but their 125 watt amplifiers are only available in 25 volts. Now this matters because the distance the circuit's able to go depends a lot on that initial pressure coming out of the amplifier. The 70 volts has a lot more pressure. It's going to be able to push a lot further. So warehouse type applications and things with really long speaker runs are ideal to have 70 volt speaker circuits instead of 25 volt because it's going to be able to travel further. Office areas and things where you might not be traveling as far do well with the 25 volt because you don't need that extra push. The 25 volt gets it done just fine. When we're doing a lot of these schools and things with these Silent Night and Fahrenheit amplifiers, we use a lot of the 125 watt amplifier, which limits us to only having the 25 volt selection. It'd be nice to have 70 volt because these schools get pretty big and those runs get pretty long. So Silent Night actually makes an additional part we can put in there that takes it from a 4-circuit amplifier to an 8-circuit amplifier. That's the ECS CE4. It just adds 4 additional circuits. So we're kind of able to overcome that distance thing by dividing the circuits in half. So we have a smaller load on the circuit. It's able to reach a little further without us having to add amplifiers. Now I do want to also mention with that ECS CE4 circuit expander, it does not add any more available wattage to the amplifier. It's still a 125 watt amplifier. It just gives us 4 additional outputs we can share it across. And then to keep moving on the slide here, for fire alarm systems, this is what the next slide is going to be expanding on this bullet point and why this topic is pretty specific to fire alarm systems instead of intercom. Even though the speakers themselves work the same way, we're going to get into specifically the fire alarm. For fire alarm systems, amplifiers must supervise the speaker circuits like NAC circuits do. Like all your strobes and all your horns, we have to supervise speakers the same way, which includes that includes T-taps. So we can't T-tap on strobe circuits because we have to pass all the way down the circuit, come across that end-of-line resistor, come back to the panel. The panel is constantly monitoring for the current draw across that resistor, and if there's too much current draw, then it's going to say, hey, there's a short circuit because there's not enough resistance here. Or if there's too much resistance, it's going to call it an open circuit, saying, hey, I'm not able to get through the circuit with the right amount of current. It's there's too much resistance. I'm not able to get enough current through it. So it's going to be supervised that same way. So we can't do T-taps and things like that. If you need to add a device, you need to add a send and return and actually interrupt the path of the speaker circuit, bring it down, and then have your return signal go and pick up where you interrupted. But instead of using a diode, if you remember when we talked about Class B circuits and strobes, we talked about how with the diodes, the current flows one direction so that it bounces off the devices, hits the end-of-line resistor, and then runs straight back to the panel. And then we flip the polarity, and the diode allows the electricity to pass through from the other direction, then lighting up the strobe. We're not doing exactly that with the speakers. There's another type of device out there called a DC current blocking capacitor. And the reason for that is the DC electricity will actually make a noise on the speakers. And so while you're in standby in normal condition, your speakers would actually be putting out like a hum kind of noise, just a constant tone, really annoying, really grating. And we don't want that, obviously. We want the speakers to be silent when they're not being used, and then we want them to turn on when they are. So this specific type of capacitor actually blocks direct current signal, but it allows alternating current through, and speakers work off of alternating current. So just like the diode is used to stop the supervision voltage from coming across, we use the DC current blocking capacitor to stop the voltage from coming across so that it can be supervised and pass through the resistor. Now, this is a very fire alarm specific thing. When you get into intercom or car audio, home audio, professional audio, all these other type of systems where you're going to use a speaker, they don't have to be supervised the same way. The supervision is specific to fire alarm because it's a life safety system. And so in all standby modes, we need to be monitoring everything to make sure it's working, the circuits are complete, everything is good, so that when the emergency does happen, the fire alarm control panel and all of our field devices are going to function and are going to safely get people out of the building. So if we weren't monitoring the circuit for the integrity, if we weren't looking for that end-of-line resistor and a wire gets cut, we'd never know it until the system turns on and, oh, hey, we don't have speakers. Why don't we have speakers? Well, it's kind of too late at that point because there's something going on in the building that turned it on. So the being able to monitor by that end-of-line resistor, that is a UL specific thing. And any fire alarm speaker that is UL listed for fire alarm use is going to have this DC current blocking capacitor already built in it. Mike has talked to me about a job that he did way back in the 90s where they took over a building that had just regular speakers in it, and they were putting a voice system in, and they had to actually add these DC current blocking capacitors to those speakers to make them work for fire alarm so that they could be supervised. Obviously, that wasn't a UL listed system doing it that way, since the devices being used weren't UL listed. But that current blocking capacitor is going to be the main thing that makes a difference between a speaker that's UL listed for fire alarm and one that's not. And it's, as far as the normal function of it, it's going to work more or less the same as these diodes do. We're not as worried about reverse polarity on these because it'll supervise it both ways, because what it's actually doing is it's blocking out DC current, not blocking out reverse polarity current. So that's going to be the difference between it and the diode as far as function goes. And as far as installing goes, it's really easy to get a speaker circuit crossed over with a with a strobe circuit because they land on the same device, on the same base, the same looking screw terminals right next to each other. But please be really, really careful that you're checking to make sure you're only pulling shielded wire for your speaker circuits, and you're only pulling non-shielded for your NAC circuits. And then whenever it comes time to trim out, make sure you're only landing your shielded wire on your speaker circuit terminals and you're non-shielded on your strobe, because doing that's going to make sure we're not crossing over our circuits. That's going to give us ground faults or short circuits on our system that we're chasing around, and we're like, why is my meter not seeing a ground? Well, because it's picking up a ground through another one of the control panels. It's not actually a short to ground. And so that can get kind of confusing, but making sure you wire it up correctly is going to keep from having those troubles. And if it is wired up correctly, like say you have the power coming off your strobe circuit landing under the same terminals as the power coming from your amplifier, and then you turn your alarm on, there's a really good chance that one or both of those control panels are about to get blown up because you're sending power to power, and you never ever want to send power from one source into power from another source. And then, so now we're going to talk about audibility and intelligibility. This can become a big rabbit trail. I'm going to try not to go too far down, but I'm going to try to stick to what you do need to know while you're installing and testing these systems. First, I've got this first column where we got some definitions we need to know, and then over in the right-hand column, there's some other points for installing it. First thing, audibility. That's going to be how loud it is. We measure that on a decibel scale. You see a couple points down, I have decibel. The definition of it is how we measure sound levels. It's kind of like saying we use inch or feet or yards to measure distance. We use decibel to measure sound level. So audibility, that's how loud it is. And then there's intelligibility, and that's how well you can understand it. And these are two things people can get kind of confused on real easily, or you can get kind of crossed up. But just to boil it down to its basics, audibility is your volume level, intelligibility is how well you can understand it. And then that last one, the acoustically distinguishable spaces, I'm going to read it real quick, then I'll talk about it. An emergency communication system notification zone that might be distinguished from other spaces because of different acoustical, environmental, or use characteristics, such as reverberation time and ambient sound pressure level. So the ambient sound pressure level, that's what decibels are. That's that measurement. When it talks about emergency communication system notification zone, it's talking about different rooms. So it's saying different rooms that have different uses or different echoes. Those are going to be different acoustically distinguishable spaces. They're regularly abbreviated in the NFPA 72 as ADS, just to shorten it. And what that kind of boils down to is different rooms in the building are going to have different code requirements for the intelligibility of the sound. So audibility is something we test a lot when we're working with horns, and you have to meet, we have to meet and beat ambient sound levels. Intelligibility is what we meet when we're working with speakers. So when we're working with speakers, the first step is we have to get the speaker to a desired volume level. And it's not an exact number on paper anywhere. It's got to be loud enough that you can hear it. And then the next step, after you can hear it, you need to make sure you can understand it. So if you can hear it, but it's getting a little muffled by things around it, maybe you need to turn it up a little bit more to make sure you can understand it. Or maybe you've turned it on and you can hear it, but it's so loud that it's echoing off of things and actually makes it harder to understand. So there are some cases where you might actually have to turn it down to get audibility where it needs to be. Another tip for when you're setting that, every time you double the wattage at the device, and this is what that other selector is on your system sensor speakers, your 1/4 watt, 1/2 watt, 1 watt, 2 watts, every time you go from setting to setting on that, your speaker output is going to increase by 3 decibels. 3 decibels is actually a pretty small amount. It's hard to explain exactly what 3 decibels is to kind of give you an example to build off of. But what you're essentially doing is you're having, every time that you do that, you're doubling the amount of power that has to come out of that speaker just to get that constant increase. So that's why, if you've ever wondered why the wattage tap goes from quarter to half to 1 to 2 instead of from quarter to half to 3/4 to 1, because that would be increasing by even wattages, but not by an even decibel output. So what we're doing is by doubling it each time, you're getting a constant increase of volume. But if you're in a room and you're looking at your meter and you're like, man, it's like about 3 or 4 decibels lower than where it needs to be, then you might just say, oh, I'm going to go ahead and bump it up 2 clicks to make sure it gets there, because that 1 click putting it at the 3 might not get me all the way to where I need to go. Then that next bullet point, if you read in the code in FPA 72, it actually has a section where voice messages are not required to meet the same audibility requirement as horn type devices. They're not required the audibility, they are required to be intelligible. And to be intelligible, you have to be loud enough to be understood. And that's why they're not at the same requirements, because they operate different way. The sound reacts differently in the room. So they came up with separate requirements for each type of system. And then that last point, there are certain acoustically distinguishable spaces, that's hard to say sometimes, in buildings where intelligibility is not required. So mechanical rooms, they're a certain type of acoustically distinguishable space. Restrooms are also another type. So you might have a school building and so you've got your hallway and your classrooms, that's all going to be one type of acoustically distinguishable space. And those spaces, we are required to have the audibility met. But there are some that, for various reasons, they know it's going to be impossible or nearly impossible to actually make it intelligible. So those acoustically distinguishable spaces do not actually require the audible notification. They only require visual notification. And mechanical room and bathrooms are going to be 2 of the most common of those, because you get all the blank sheetrock walls with the hard stall wall doors, and you get the tile floors and the hard ceiling, and sound just bounces off of that, and there's nothing anywhere in the room to stop the sound from bouncing around. So you get all that reverberation just bouncing and bouncing, kind of muffling the sound, making it harder to understand. And so the code writers knew that when they were writing that, so they wrote this in there so that places like bathrooms that have all of that echo going around aren't actually code required to have intelligibility. They're only required to have a visual notification. And then mechanical rooms, mechanical rooms don't have that same problem. What they actually have is they have a loud ambient volume that's hard to overcome. And that's from the different mechanical equipment in there, like your air handler units, your chillers, maybe your water heaters or cooling fans, things like that. Anything that causes that ambient sound level to get above a certain decibel level, they say once you reach that threshold, you're no longer required to actually be intelligible anymore. And so they just want visual notification in there. Now, there are a lot of schools where we still end up putting speaker strobes in there instead of just regular strobes. That's typically because there's an engineer or an architect that wants a speaker strobe in there, even though it's an acoustically distinguishable space. So we put it in there, that's what they want, or it's what the customer wants, but it's not actually required to meet that intelligibility level. We typically just turn it up to try to make it where you can at least hear it so you know something's going on. If we can make it intelligible, that's fantastic. Let's go ahead and do that. If we can't, it's not code required, so don't lose any sleep over it. I think that's basically it to talk about acoustically distinguishable spaces. Also, rooms, it's not just limited to mechanical and bathrooms. There are other rooms that apply, like if you've got a room that is all cinder block with hard ceiling and a concrete floor, that's probably going to be an acoustically distinguishable space. So if you're having problems getting to your desired intelligibility there, acoustically distinguishable spaces of that sort don't require intelligibility. They just require visual notification. Now the next couple slides I copied straight out of when we talked about Class B circuits, and this is how to use your meter to test your speaker circuits. hold on, why aren't you changing? Okay. So we're going to test it the same way we test strobe circuits. Before we land the wires to the panel, we're going to check them with our meter using the ohm setting. And we're going to connect the red lead to the red conductor and the black lead to the black conductor. And we're looking for our end-of-line resistor. If we see our end-of-line resistor, everything's good. And then we move on to where we check for ground fault, like we talked about recently, where you put 1 meter lead on your earth ground, and then the other meter lead, first you check one side of the circuit, then you check the other side of the circuit. You should see no continuity to ground. If you can see your end-of-line resistor and you don't see any ground reference, that circuit is free and clear. You should be safe to hook it up to a panel. If you see a short circuit, then you're going to, well, here, I'll go ahead and go to the next slide. You're going to troubleshoot it the same way where we talked about dividing the circuit in half and trying to work back and forth. That's all going to work the exact same way that troubleshooting a strobe circuit would work. And that actually puts us right at our 30-minute mark. So if y'all have any questions or anything I said that might be confusing or that you want to revisit, now is a great time for that. If you don't have any questions and you're like, no, I'm good, then you're free to go. Thank you for being here. I appreciate y'all's time. I hope this helps y'all out in the field. And yeah, if you have any questions, let me know.
Keith, I sent you a text message with some questions on it.
Okay, let me pull my phone out. Okay, first question that Colin sent me is, why is it important to make sure that our taps are correct? So those, first I'll talk about the voltage taps, then I'll talk about the wattage taps. It's important to make sure your voltage taps are correct because that changes some internal wiring in the device so that your speaker actually puts out the right amount of sound and the right clarity. So if you're running a 70-volt amplifier and you've got it set at the 25-volt setting, which is the default setting on the device, you're going to be overloading that speaker driver, and it's going to come out very crackly and distorted, and you're not going to be able to understand it because you're actually overpowering your device. And then if the reverse is true, say you set it for 70 volts, but you've actually only got 25 volts coming out of your amplifier, it's going to be incredibly quiet because now it's wired through a circuit expecting more power than it's getting. So you need to make sure that your voltage tap is set at the same as as what your amplifier is putting out, so that you get the right amount put out. That's going to help with the clarity and the volume level. And then as far as wattage taps, that's a little more fine tuning, getting us in the right neighborhood. That's going to tie into that intelligibility thing we talked about. Because if you're not loud enough, you're not going to be able to understand it. Or if you're too loud, you're not going to be able to understand it. So you got to get right in that sweet spot where you can hear it and understand it. Second question, Colin texts me, says, what should you check if you were doing a speaker add to an existing system? Okay, that's a really good question. So it gets a lot into the math with Ohm's law. You can actually wire your meter in series with the circuit and set it on current draw, and you can see what the current draw of that circuit is. And you can use Ohm's law to work through the math. And we haven't talked about any of the math in here. Mike actually, he asked me not to. He says it was a really big thing, but I think as we get more and more technical, we're getting closer and closer to really needing to start talking about that math and how Ohm's law works to keep going deeper into how this goes. But you can use your meter with the circuit running. You can see how much current draw is on the circuit, and you're able to work it through the formulas in there. And people have actually made online calculators if you don't want to deal with the formula. And it'll tell you how much wattage you're currently using, and then you'll compare that wattage to the wattage capability of the amplifier. And then what can happen during an emergency if an amp gets overloaded? So an amp getting overloaded basically means there's too much current flowing through it. Current is the part of electricity that creates heat. So the more current you push through something, the hotter it's going to get. And so the amp getting overloaded, it's overheating. So the amp can actually burn itself up. So it has a silicon circuit board on it. And then all the components are soldered on with a type of metal that has a very, very low melting point. So it is possible to actually get that circuit board so hot that the solder starts to melt off and your components start to fall off. And your amplifier will actually have physical failure. The circuit won't be complete anymore. You won't have any more audio output. There are some amplifiers that are actually designed and built so that even when they get overloaded, they have a backup amplifier in them that tries to help share the load. Our Silent Night amplifiers and our Game Wall amplifiers are not designed that way. I know Notifier has one that does it. And Silent Night makes a 100-watt amplifier that you can set up to function as two 50-watt amplifiers. So you have your normal 50 watts, and then you actually have a 50-watt backup amplifier built into it. We don't use that one a whole lot. When I'm designing fire alarm systems and I'm laying out these circuits, I actually I have a rule of thumb I use to try to help us from overloading it that I don't even know that y'all know I do it. I derate all of them down to only use 80% of what the amplifier is capable of. So on a 125-watt amplifier, that means I only use 100 watts. If I exceed that 100 watts, that means I need another amplifier. And on 50-watt amplifiers, I only take it to 40 watts. And so what that does is it gives y'all some headroom out in the field so that if y'all have to turn a speaker circuit up or down from what I've set it at on the plans to maybe match the really make the speaker fit the requirements of that room, it gives you some headroom to play with that where we're not worried about overloading it. And it also gives us some room for the amp to grow in the future if they want to add a T-building with a couple devices or something. Okay, those are the 3 questions he texted me. Do those answer them for you, Colin?
Yes, sir. That's what I was looking for.
All right, thank you. Does anyone else have any questions? Those were really good questions. I'm glad you asked those. Does anybody else have any?